Hello everyone, and welcome to our 24th lecture for MAT353. This is the lecture for Friday, April 3rd. The first part, we are going to be talking about integrals in polar coordinates. So first, let me apologize for the gray line that's running across all of these pages. There's apparently an issue with my scanner. I will try to rectify it, hopefully be able to do so, as we need this scanner for the rest of the term. But beginning to think about integrals in polar coordinates, we introduced polar coordinates last time. The idea is that you can designate points in the plane by using an r theta ordered pair instead of the xy ordered pair we have traditionally used. We took a look at what rectangles, quote-unquote, look like in polar coordinates to get some sense of which types of regions are most naturally expressed in polar. And also to that end, we looked at the grid lines that are formed when you set either of the variables equal to constant values in polar coordinates. The purpose of all of this is to turn hard problems into easy problems. That is the bulk of what we do. And the reason that polar is useful to that end is that some regions are more easily expressed in polar coordinates than they are in Cartesian. So as an example of that, let's let R be the region bounded between the circle of radius 1 and the circle of radius 2, centered at the origin. I don't actually say centered at the origin here, but that is what I intended. And we want the portion lying between those two circles, which also lies in the first quadrant. And we are directed to express this region both in rectangular and in polar coordinates. So I draw the region first. I draw the northeast corner of the circle, the northeast quarter of the circle of radius 1 and the northeast quarter of the circle of radius 2 centered at the origin, and I shade the region in between those curves in the first quadrant. It does seem like polar is going to be the more natural way to express this region, so just looking at it, it has what is essentially a circular shape to it, and polar is generally going to be preferable to describe regions of that type. But we've been told to try rectangular and polar, and we'll go ahead and try rectangular first. So the problem with expressing it in rectangular, or one of the problems rather, is the fact that if I'm thinking about letting x slide from one value to one value, so I'm going to express this as a type 1 region here. I could easily well express it as a type 2. But thinking about expressing it as a type 1 region, I would be letting x go from 0 over to 2 here, the largest x value associated with a point in this region. But where y is going from and to changes as I cross this vertical division that I've introduced. So to the left of this vertical line, y would be going from the inner circle up to the outer circle. But to the right of this vertical division, y would be going from the x-axis up to the outer circle. So that's why I dropped this vertical division. I'm going to name these two regions R1 and R2. R will ultimately be made up of their union. We haven't talked much about set theory operations. The union just basically means take these two regions and stick them together. So take all the points that's in either of them and combine them into a union. I can describe R1 as a type 1 region relatively easily. For R1, we're taking xy ordered pairs such that x is going from 0 to 1. That's x going from the y-axis over to our vertical division line here. And then for each of those x values, y will be going from the inner circle up to the outer circle. So we've got y going from the positive portion of the circle of radius 1 over to the positive portion of the circle of radius 2. And then in the region R2, x is now moving from 1 to 2, which I have here, and y will be going from the x-axis, y equal to 0, up to this outer circle. So y is going from 0 up to the circle of radius 2 here. And then I have to take the union of those two regions to get all of r. And none of this is great. These are already ugly expressions for R1 and R2 themselves. They involve elaborate square roots. Anytime you're seeing these kinds of square root expressions, this is the type of thing that happens when you attempt to express circular regions in Cartesian. You end up with the square root of the radius squared minus one of the square variables. And that's generally not great. So neither R1 nor R2 is expressed nicely in Cartesian, and then we actually have to take their union to get all of R. So it's doable, but it is a bit cumbersome. Instead, if we attempt to express this region in polar, it turns out to just be a polar rectangle. Both of my polar variables are going to be bounded by constants here. We've got r going from r1 to r2. That shows us pushing out from the origin to the closest any of the points in this region get to the origin, which is given by the curve r equal to 1. out to the furthest that any of these points get from the origin, which is given by the curve r equal to 2. So we've got r going from 1 to 2, and we've got theta going from theta equal to 0, which gives me the positive x-axis, rotating up through theta equal to pi over 2, which gives me the positive y-axis. So you can imagine a flat beam that's anchored here at the origin and sticks out along the positive x-axis, and that beam rotates up through an angle of pi over 2 to be able to describe every point in the region. It's like a windshield wiper blade, moving from a down position to a fully vertical position here to describe the theta values. So expressed in Cartesian, it was one of the more annoying regions that we've ever tried to express in Cartesian coordinates. And expressed in polar, it is as simple as it could possibly be. Both variables have constant bounds, and in fact this is a rectangular region in polar coordinates, what we also call a polar rectangle. So sometimes it is certain regions will be much more easily and naturally expressed in the appropriate coordinate system. This is going to amount in some sense to coming to the problem on its own terms, approaching the problem in its own way, in the respecting the nature of the problem itself and not trying to impose an unnatural coordinate system onto a region that is expressed much more naturally in a different one. So let's have you folks think about a problem here quickly. Let's let big R be the left half of the unit disk centered at the origin. Express that for me in either polar or Cartesians. I'm not asking you, or Cartesian coordinates. I'm not asking you to do both. I'm asking you to pick which region seems best and express it in that, rather, pick which coordinate system seems best and express this region in that coordinate system. Go ahead and pause the video and give that a shot. Alright, so let's have a look. Polar is for certainty going to be best here. It can be expressed in Cartesian, and I'd be happy to show you in office hours. It's not that crazy. But polar will be definitely the most natural way. So r equal to 0 represents just the origin, the only point that is distance 0 from the origin. We're going from r equal to 0 up to r equal to 1. If all I gave you is the top line here, that would be a characterization of the unit disk centered at the origin. Instead, I'm specifying that we only want a portion of that disk, as I'm telling you that we only want the theta values from pi over 2 to 3 pi over 2. So theta is starting here at pi over 2. My windshield wiper blade is beginning in the fully vertical position, and it's actually going to rotate around this way until it reaches the negative y-axis here. And that's given us the left half of the unit disk that we've described. So in general, this expression for theta gives you the left half of the plane, combined together with this expression for r, which gives us the unit disk, and we get that portion of the unit disk which lies in the left half of the plane. Questions are always welcome, so feel free to email me, contact me if you have any questions. Ultimately, we want to begin to integrate over regions expressed in polar. It's nice to be able to describe regions, but this is a chapter that we are studying on multiple integrals, multiple dimensional integrals, and so the goal is to be able to integrate over regions when those regions are expressed in polar. And in order to do that, we have to figure out what the dA expression looks like in polar coordinates. When we thought about Cartesian coordinates or rectangular coordinates, it was relatively easy when we formed our two-dimensional Riemann sums to think about the delta x expression. This was a change in the x direction, and the delta y expression. These were sort of the dimensions of the grid that we imposed in the xy plane. And then we had a delta A expression that was going to be the area of the base of each of our rectangular boxes that made up our Riemann sum. And delta A was easy to see. It was easy to see that delta A was equal to delta x times delta y. And then in the limit, as those Riemann sums become more perfect, as we take more and more terms, the delta A term becomes a dA term equal to dx dy here. So a finite approximation, you take a limit, you get the exact expression. But this delta A equal to delta x delta y became our dA equals dx dy that we've been working with to date. In polar, the situation's a bit more complicated because the grid is a bit more complicated. In Cartesian here, the grid remains uniform no matter where you are in space. It's always a delta x width, and it's always a delta y height for each of these grid boxes. In polar, things are actually going to depend on your absolute position in space. And to see that, we've drawn this picture. So here I've got several theta equal to a constant lines. And the move as we rotate it is this branch here rotated up to that branch there, that we're calling delta theta, a change in theta. Likewise, we've got these portions of circles which represent r equal to some constant value. And as we move from an inner circle to an outer circle, we're getting a delta r expression, a change in the radius. So these points are all some distance from the origin. These points are some greater distance than the origin. The difference between those is our change in radius. And then I'm going to highlight two of these little boxes, quote unquote, two of these little grid elements. So I'm going to call this one A1 for the area 1, and this one we'll call A2 for area 2. We're going to extract those, and we're going to consider them in isolation here. And this is not necessarily to scale, but it's drawn in such a way that we can see here's the theta equal to constant line, here's the other theta equal to a constant line. The change in the radius here, if I think about these as boxes, then they're going to be something like a width and a height associated with both of them. The height is the delta r expression, effectively. So the height of these two doesn't change. The height is the same delta r for both of them. You're just moving some distance along one of these diagonals, for instance. Whereas the width, it's clear here in the exaggerated picture that I have drawn that A2 is far wider than A1 is. And so the width actually changes, is larger for A2. The width increases as you move further away from the origin in the picture above. A1 is closer to the origin, and for that position, the change in theta does not sweep through such a wide arc as it does for a position which is further from the origin. This is analogous to the idea that if you swing a baseball bat, the portion of the baseball bat that's directly above your hands does not move through as wide an arc as the tip of the baseball bat does. If I take a 20-foot pole and I hold it straight out and I rotate it, the portion of the pole that's close to my hands moves through a relatively small arc, where the tip of the pole is going to sweep through a very wide arc. The same idea is happening here. So the width, quote unquote, of these boxes depends on how far from the origin you are. And in fact, that width is going to be given by delta theta times r. So if r is bigger, we're getting a larger width, and for r equal to a smaller value, we get a smaller width. So the area of these boxes, sorry, wrong way. The area of these boxes are going to be height times width, roughly. We're fudging the geometry just a little bit, but this is actually how it works in the limit. So the area of each of these quote-unquote boxes is something like height times width. I can rearrange that and write it as r delta theta. I take a limit. My delta A turns into a dA expression. I just realized I've left my aquarium air pump on again. So sorry, that should kill an annoying buzz. But my dA expression here, my delta A becomes a dA expression, and dA is going to be equal to r dr d theta in polar coordinates. So at this point we can summarize the main salient features of both of the coordinate systems for the plane that we've studied, Cartesian and polar. In Cartesian, your variables are the xy variables, and your dA expression just looks like dx dy. That's generally all that you need to be able to integrate in Cartesian. In polar, our variables are r and theta, and the dA term looks like r dr d theta. And again, this is a nice summary. It gives you sort of the gist of the coordinate system and almost everything that you need to know to be able to integrate in it. You might also have to remember how to translate between r and theta and x and y, for instance. But this is something that I would have on a summary sheet as we go through and think about different coordinate systems. We're going to move next into thinking about three-dimensional integrals. And for there will be 3 different coordinate systems. But for each coordinate system, it makes good sense to keep straight what are the variables and what does the dA or dV expression look like, depending on if you're dealing with 2-dimensional or 3-dimensional regions that you're integrating over. So another brief aside here, this idea that dA becomes r dr d theta, this is an example of a mathematical phenomena that is known as change of measure. So there is a change of measure theorem. There is a special case of it which your book discusses briefly that's called change of variables, and that's sort of a practical special case version of change of measure. But the idea is that you can shift the way that you view space, right? Here we're shifting from the rectangular grid lines of the Cartesian coordinate system to these spider web looking grid lines associated with the polar coordinate system. And as you change your perspective on how you divide up space and how you measure it, you have to keep straight how the idea of area changes. So the way that you measure space can depend on the way that that space is viewed in some sense. In Cartesian coordinates, the way that each little unit area is measured was always delta x times delta y. But in polar coordinates, the way that each little unit of area is measured actually depends on how far from the origin you are. So there's that r factor involved in the dA expression. And you can oftentimes shift your perspective on how space is represented in order to simplify certain problems. But if that does change the way that area is measured, you have to keep up with that. You have to take that into account, and that's why the dA expression here involving the r term is going to be necessary to accurately integrate in polar coordinates. And we will do that now. So we're going to have a theorem here about how to perform double integrals in polar coordinates. So if you have an integrand expressed here as a function of x and y, and it's continuous over a polar rectangle of this type, so we've got constant bounds for r and constant bounds for theta, then the double integral of f over that region is going to be given as an iterated integral, which we're taking here with respect to r first, and then with respect to theta. And your x value is getting replaced with the expression for x in terms of r and theta, r cosine theta. Your y value as the input to f is getting replaced with an expression in terms of r and theta. Your dA term turns into r dr d theta. So we're not just integrating f here, we're integrating f times r at this point. And that is how you perform integrals in polar coordinates. We'll see examples shortly. So lots of notes, lots of things to bear in mind here. The first is this extra factor of r. Very common mistake for students who are just learning this material to forget to include the extra factor of r that polar coordinates introduce. So you do pick up a new factor for your integrand, this new multiple of r that's introduced to the integrand when you switch from rectangular to polar for the expression of an integral. And r here is a polar rectangle for the second note. There do exist what we would call type 1 and type 2 polar regions, so the types of regions that something analogous to what we studied when we were thinking about Cartesian coordinates and integrals in rectangular coordinates over more general regions. We studied these type 1 and type 2 regions where only one of the variables has constant bounds and the other variable's bounds are allowed to depend on the first variable. There exist analogous regions, and your book discusses them briefly. Our focus is going to be on polar rectangles here. So we may touch on a few of those regions in some contexts, but our focus will be on polar rectangles. Generally, in switching from a rectangular integral to a polar integral, from an integral over a region expressed in rectangular to an integral over a region expressed in polar, there's a benefit-cost analysis. The benefit that you gain is when the region is more naturally expressed in polar than it would have been in Cartesian. So maybe you had a bunch of nasty square root symbols floating around your limits of integration when you tried to write the integral down in Cartesian, but then all of that dissipates and you get nice, lovely, constant limits of integration when you express the region in polar. That's the benefit. It simplifies the description of certain regions. The cost you pay for making this transition is the introduction of this extra factor of r into your integrand. So switching from Cartesian to polar can simplify the limits of integration, but increase the complexity of the integrand itself. And so there's a balance in that. It is also true that sometimes the extra factor of r that you introduce into the integrand is actually helpful for you. So sometimes you may be by introducing a factor of r, you make a u substitution possible when no such u substitution was possible before. And this will make more sense likely after we look at some examples, but sometimes this cost listed here is actually also of benefit if it opens the door to an integration technique that would have otherwise not been possible for the problem. And the fourth note to make is that just like in rectangular coordinate systems, when all of the limits of integration are constants, Fubini's theorem is going to tell you that you can switch the order of integration freely. So you can simply rearrange the order It's much simpler than the case for type 1 and type 2 integrals, where you actually had to do some thinking and some work to be able to switch the order of integration. Fubini's theorem for polar rectangles tells us that the rectangle here, this is a dr d theta iterated integral. The innermost integral has our limits of integration, our bounds for r. Here we see the bounds for theta. If we want to rearrange that to a d theta dr integral, we just have to make sure that we switch the limits around as well so that they remain corresponded to the appropriate variable. But there's none of this go from the limits, draw the picture, from the picture re-express, and then go to your other limits nonsense that we had when we thought about switching the order of integration for more general regions in Cartesian. So hopefully that all makes sense. This formula is the main thing that we're considering here today. So this is the big important formula for actually performing integrals in polar coordinates. And the next thing that we'll do is look at some examples and think about some sample problems for these types of integrals. When my mouse starts working, we will stop the video.